Hello again. I'm back to continue the lecture on magnetism. So I'm going to start from where I stopped last time. So I just want to get started from here. So last time we introduced LS coupling. Then we calculated the contribution coming from the term L dot S, that is the angular momentum and spin angular momentum coupling. So if you look at these L and S, so we know the total magnetic moment M, so that is given by minus mu B, 2S plus L, right? Because 2 is the gyromagnetic factor coming from with S. So here we have factor 1. So but now if you write 2S as S plus L, so then you have 1 S plus L become J, then you have this one you can write as J plus S. So now this is a complicated system. We know how to calculate the quantities from S and L. So but we cannot directly calculate for J because you have even the term coming from S also. So then this is becoming a little complicated. So also we know the M is not a constant of motion, right? So because J is constant of motion but not S. So but here we have both J and S. So that means M is not a constant of motion. So also we know this H total Hamiltonian and J, they don't commute. So you have then if you write J as L plus S, so we know both L and S precess about J. So then also J is precessing about the B magnetic field. So if you look at here, you can see L here and S here. So they both precess about J vector. So then the J vector is going to precess about the magnetic field B. So this will allow us to calculate this the something called Landé G factor that's coming with this total magnetic moment J. So because if you remember, for orbital angular momentum, we write mu L as GL mu BL. So then GL was 1, if you remember. Then mu S due to the spin magnetic moment. So that is GS mu BS. The GS was 2. So now we need to calculate what is the net magnetic moment mu J. So that should be G times mu BJ. So the whole idea is to calculate this G. So then also we know how to calculate this eigenvalues of L squared, S squared. So that will help us to calculate this G factor. So whole idea is, so if I have a magnetic field in the direction of J, so then I can write my total M as this minus mu B J plus the parallel component of your S value, right? You can understand that because this is L, this is S, so this will be J. So then if you take the vertical component of S, that is S parallel. So if you subtract that one, that is J plus S parallel. So we need to calculate the values corresponding to this J plus S parallel value. So that's we can calculate using, because how do you calculate? So J we know how to do, but to calculate S parallel, what we do is you just multiply S by the unit vector in this J direction. That's the direction of B. So then also we know how J is we can write S in terms of this J squared minus L squared plus S squared divided by this 2J squared in the direction of J. So now, since we know the eigenvalues for j squared, l squared, and s squared, that is jj plus 1, ll plus 1, ss plus 1 divided by 2 jj plus 1 with j vector, right? So that is the component along s parallel. So then we need additional contribution coming from j. So this is also j. So then you get additional factor 1 in addition to this s parallel. Then your total value m you can write as like here minus mu b. So then this is your g, right? So because this factor plus 1 coming from this j here. So we call this one lambda g factor, that is function of both the total angular momentum, total spin angular momentum, and total the sum j factor. So then this is called the lambda g factor. Then you know how to calculate your total angular momentum in terms of your total angular momentum. So now this can help us to develop these Hund's rules. Everybody remember Hund's first rule is actually we can make the total S to be maximum, because we know if you take these rare earths and transition metals, their ground state and the excited states are very different. So their energy difference is very high. So that means we are talking about something like 10 electron volts. So then we are only interested in calculating the values for ground state, because the excited states are too far from the ground state. So then, like I said, your rule number 1 is each electron up to 1/2 of the states in the shell contributes like half S values. So then beyond that one, it contributes -half, right, when they feel the downspin one. So we'll do all these once. So this is how we know how the orbitals are filled. First 1s, 2s, then 2p, 3s, then 3p, 4s, 3d. So in this order, right? So that's the I think reason is this Hund's rule. So that helps us to study how these orbitals are filled. So then we know second rule says your total angular momentum L should be maximized. Once the total spin angular momentum is maximized, then your L should be maximized. So that depends on what kind of electrons you have. If you have d shell electrons, so that means SPD, that means d is 2, then you can have L going from -2 to +2, right? So you have -2, -1, 0, like that. If you have F shell, F is SPDF, that is 3. So that means it will go from -3 to +3. So then if you have 2 electrons with the same spin, cannot make the same contribution, right? So that's what. So that's number 2. Then the Hund's rule number 3 is, so if your orbitals are less than half full, your capital J is L minus S. Depending on what is larger, you have to take the absolute value of that difference. So if it is more than half full, J will be L plus S. If it is exactly half full, it is J equals S, obviously. So let's do a couple of examples. So let's start with these 2 examples. So this we call the praseodymium. So PR, so iron, so that has 2 F electrons. So then we'll talk about erbium that has 11 F electrons. So if you first start with this PR with 2 F electrons, so what do you know about this? F means SPDF, that is 3, right? DF, yeah. So that means you can have L values going from +3 to -3. So if I put all these boxes, you have 7 of them, right? So now you have only 2 electrons. So how do you fill this one? First, you need to make sure you are filling so that your total S should be maximized. So that means it should be up and up, right? You cannot have 2 up ones. But if you can put down one here, but then your S is not going to maximize, right? If you put S here, total S will be 0. Then maximum S you can get by putting all the ones up direction. So then once that is satisfied, your total L should be maximized. So how can you maximize S? L. So then it should start with this highest L value, right? +3. Next +2, then +1, like that. So this is the way it satisfies both maximum S and maximum L. So now you can calculate what is the total S. So what is total S? You have 1 in this direction, 1 in this direction. That means 2 times half, right? So that means it's 1. The half and half. Your total S will be 1. Then what is the total L? You have +3, one of them, right? So only 1 electron. So that +3. Then you have another electron with +2. Then your capital L will be 5. So now, if you look at this one, so this is only less than half filled, right? So half is here. So less than half filled means your J will be L minus S. L is 5, S is 1, then your J will be 4. So now, if you want, you can calculate your Landé G factor, right? So remember, Landé G factor is given by this expression, 1 plus this whole thing. We know now J, L, and S. Just plug in those numbers. J is 4, 4 times 5. You can see then S is 1. So if you calculate this one, you get Landé G factor as 0.55. So then if you want to write this one in this spectroscopic notation, so you have L is 5. L5 means 0, 1, 2, 3, 4, 5. That is H, right? So this should be H. So then here S is 1 means 2S plus 1 is 3. So then J is 4. So this is the spectroscopic notation, 3H4. So now let's look at another example. So this is for erbium. Erbium has 11 still F electrons. F means again SPDF is 3, right? So you have +3 to -3. So because you have 2L plus 1 states, right? So now what you have now 11 electrons. So how do you fill this? First you need to fill so that your S should be maximum. That means you put all in upward direction, right? So that's 7 of them. So now you cannot put any more ups. Then only thing you can do is put in them downwards. So down 7, after that 8, 9, 10, 11, because you cannot have 2 electrons spin up or down, right? They have to be either up, one up and one down. You cannot have both up or both down. So because that's the Pauli exclusion principle. So this is the only way to maximize S. Then also, if you want to maximize L, you have to start filling from this +3, right? That's the highest value, +3, +2, like that. So then this is the way you can maximize your S and L. So that satisfies your Hund's rules 1 and 2. So now you can calculate your total S. What is the total S? You have 7 S plus ones, right? Upward one is +7. That means 1, 2, 3, 7 of plus half. Then you have 1, 2, 3, 4, 4 of minus half. So if you add this one, you get S as +3/2. Then what is your total L? L is you have 2 of them with 3, right? So that means +3 times 2. So then you have +2 times 2 electrons here. Then you have +1, 2 of them. Then you have +2 of, sorry, 0 of 2, because you have 1 and 2. So they both have this number 0. So that 0 times you have 2 of them. But here you have -1 times only 1. 1 times -1, then 1 times -2, because only 1 of them, 1 times -2, 1 times -3. If you add all these things, you get L equals 6. So now you have capital S, capital L. Now how do you calculate J? Now if you look at this one, this middle is your half, right? So now this is more than half filled, because if this is more than half filled, that means your Hund's third rule says your J should be L plus S, because L is now 6, 6 plus 3/2. If you add, that is 15/2. Now you have S, L, and J. Then you can calculate your Landé G factor using this equation. You get 1.2. So now if you want to write the spectroscopic notation for this one, what do you get? So because L is 6 means 0, 1, 2, 3, 4, 5, 6. That is I. Then S is 3 by 2 means this is 4, right? 2 times 3 by 2 is 3 plus 1 is 4. Then J is 15 by this is the spectroscopic notation. You should be able to do all these examples very easily. Okay, so now let me remind you what we learned so far about this diamagnetism based on quantum approach, right? So we know this term, so that is coming from that Lama precision, right? So remember, actually, corrected version is this should be 6 here, but this is general relationship. The corrected version you can put 6 here. So then we have this contribution coming from spin angular momentum and spin angular momentum two terms. You can see this gyro magnetic constant here too. So this actually ideally you can write EH cross here. So that's a Bohr magnetron, right? So this is a classical way of writing that one. So then also ideally, that's what I said, you need to correct for this one, then this becomes 6. In quantum approach, you have H cross here, right? So now if the B is in the direction of C direction, then your mu becomes basically LC plus 2LC, right? So then this is x squared plus y squared. Then if you want, you can calculate this expectation values for LC as your wave function LC is 1. We know SC is always plus or minus half H cross. Then somebody can calculate this function also by calculating this expectation value like that. These simple things to do. So that's basically what we were talking about, diamagnetism, right? So now I want to talk a little bit this co-paramagnetism. Still we are talking about the atomic or ionic contribution. So if this both the LC and the C expectation values, if they do not both vanish for an atom or ion, that atom has permanent magnetic dipole moment, right? So then you can have something called the paramagnetism. So far we were talking about this diamagnetism, right? So then we'll see how we can calculate that co-paramagnetism. So some examples are this gadolinium chloride, iron fluoride. So they have this paramagnetic properties because of they have this permanent localized magnetic moments. So that co-paramagnetism we call is the Curie paramagnetism. So we talked about initially the Lama diamagnetism. Now we are talking about the atomic configuration giving rise to the paramagnetism. So that is called the Curie paramagnetism. So like I said, we have this JC and SC values non-zero. So that will give you this co-paramagnetism. So if I write just the total magnetic moment, so if you have your magnetic field in the C direction or in the in the C direction, you can write your mu C as minus G mu B Z JC. Sometimes since we are putting that H factor here, so then you can divide it by H cross. Some books they write it this way. So then we can write this factor as this MJ. So because JC is given as, if you remember, M times your H cross, right? So the eigenvalue of, remember, J squared is given by square root J plus 1 H bar squared. So similarly, JC is given as MJ H cross. So if you do that one, you get this is simply MJ, that quantum number mj. So now, so this is mu c. So because of this one, that's what I was trying to explain. So because h cross m, so that's why you get this one here. So then this is the magnetic moment. So then what is the magnetic energy? So you just mu dot b, right? So if you calculate, but that energy is mu dot b, that mu c b. So that you can write as, so negative term, they cancel each other, b times b. So that is your energy. So now if you have a bunch of these dipoles, so you need to calculate what is the total magnetic moment or average magnetic moment. So we know, so if we have some at certain temperature, so these magnetic moments can be distributed randomly, right? So you then you need to calculate what is the average magnetic moment by using this simple Maxwell-Boltzmann distribution. So how do you do that? So then you have to add all the first, since you are calculating the mu c, you need to calculate mu c. So this is mu c value, g mu b mj, but they have probability of Maxwell-Boltzmann. Everybody remember that's E minus E energy divided by kBt, right? So the energy is now mu b mj times b. So actually G should be here, sorry. So that is the Boltzmann Wayne factor. So then divide by the your Boltzmann factor without the energy part here, right? So it's this basically E minus beta E divided by E minus just beta without your energy, right? It's only the mu E terms you can get. So this is your average mu c. This is the Boltzmann factor divided by this normalization constant. But mj, remember, that goes from minus j to plus j. So because you have 2j plus 1 states, right? So if you do this one, actually it's not very difficult. This is a standard expression. So if you the summation you can do, this is actually, if you differentiate this one, you get this function, right? So then using some simple summation expression, you can get this one as this function. So this is beta j that has the argument of this one. So this beta j is called the Brillouin function. So this is basically that has the component of cot. So cot is basically cosh over shin, right? So I think everybody should be familiar with that one. So that is your mu c, that's expressed in terms of this Brillouin function. So then you can, so this yeah, so then you can write your that is mu c. Then how do you calculate the magnetization? So then magnetization is the total number of magnetic moments per unit volume. So if you have n number of moments per unit volume, just multiply by n, then you get this function, right? So the beta j, remember, that's any beta, the argument is this one, so that is x. So then you have this. So that's general definition of Brillouin function. Okay, so typically if you plot this Brillouin function with x, so they show this kind of behavior for different j values going from 1, 3, and 5. So you can see the Brillouin function, they, for high x values, they approaches 1. So they approaches a constant value 1, but for low x values, they are pretty linear. So we can easily approximate that one. So that we are interested in low x values. So that's linear region. Then high x values, that's reaching 1. So that's what we are interested in. So this all coming for the paramagnetism, because your magnetization is a positive value. So now if you consider the situation, this term, this G mu B JB is much greater than this KBT term. So this KBT term is nothing but the thermal energy, right? So that means if you are at not very high temperature, if you have your B is much larger, that's a magnetic energy, right? That is much larger than your thermal energy. That means all the ions will be in the lower state because they all try to align in the direction of B, because thermal energy, if without B, so all the magnetic moments will be randomized, right? Because it's a thermal agitation, right? So because of thermal energy, they are pretty much randomized, but by applying large magnetic field, so they all align in the direction of B. That's why we call it paramagnetism. So that will bring all the electrons to the lower state. So then at that region, so X is very large, then the Brillouin function reaches 1, right? So then in that value, your magnetization is given by Ng mu B times J. So that is true for low temperatures and very high magnetic fields. But if your magnetic field is small and the temperature is much higher, so then the electrons, they don't care about the magnetic field because of the ions. So they have high effect from the thermal energy. So they like to be in those different orientations with the same probability, right? So that means magnetization will be very small because they are not going to align in particular direction. So that means your X is going to be very small. So that's why we have the Brillouin function shows this linear dependence, because then you that has linear dependence, like as we saw in that plot. So if you in that region, you can show your M is given by this function. So in the because your X has this JJ plus 1 terms and everything. You can see the two limits in the low temperature and high field. You have this constant value, but in the high temperature and small magnetic field, that shows temperature dependent. This is temperature independent, right? So that's what important. This gives rise to something called the Curie law, because M goes like some constant divided by T. That's very important thing. So because your susceptibility is mu0 M over T, if you divide that one, so this shows this T, because this C is that long expression, right? J is the total angular momentum, L plus S. So these are all we know. N is the number of atoms per unit volumes. Mu0 we know. Mu B is the Bohr magnetron. Kb is the Boltzmann constant. This C is a constant, but chi is given by C over T. So that shows this 1 over T behavior. But the susceptibility reaches very high values for T0, right? So it's an asymptotic behavior. So the Curie constant is given by this value. So then we define this, if you write this one in this form, we can write this P here. So this P is the effective number of Bohr magnetrons per ion. So if you write this one, this you have mu0, mu B squared over Kb. So then this P is given as this J plus 1. Yeah, so this is P. You can write this function, right? J plus 1 G. So P is basically 1/3 is already there. P means G squared. So P squared means G squared J plus 1. So because you can see rest are all in here. So that is nothing but the effective number of Bohr magnetrons per ion. So now if you look at this figure here, so this shows you the p value. That what is that p value is that G squared, J plus 1, that is P squared, then P is G square root of J plus 1. So now if you look at different ions, mostly these rare earths, so you can see, so these are their electronic configurations. So this is the spectroscopic notation. So you can calculate for these ones your p-value. If you know capital J and G, you can calculate your p-value. Now we already did, if you remember, we did these two examples. We did for this PR and also erbium, right? Erbium. Remember erbium, when we did, we had 4 11 F electrons. So then we found this was our notation, right? For I 15 by 2. That's the second example we did. So that means you have J is 15 by 2. So then you can put 15 by 2 plus 1. Then also we calculated G, the Landé G factor. That I remember it was like 1.2 or something. So now if you calculate that p-value, you get 9.59. But experimentally people measured that comes very close to that value. So for all these values, people have calculated the p-value. So you can see in this case, your p-value, since J is 0, it is 0, right? So, but experimentally that is a little bit off. But other than that, I think they are very close. Okay. Now this is the Curie paramagnetism in limiting case. Remember, in the case where X is small, so you have linear region. So that happens when T is small, right? So when you have T small, you get this constant magnetic moment. For in this region, we also showed your susceptibilities going like some C over T, right? So sorry, yeah. So that is for yeah. So then for low temperature region, we had chi given by C over T, then C is given by this expression here. So that is for remember this is KB over T. So but when you have very so this is for low temperature, right? So that's what we calculated. So then also so if you summarize this one, we can say the atomic diamagnetism we showed that is always true, right? That's coming from the Larmor precision. Then this paramagnetic behavior comes from non-filled shells, right? So that is coming from these unpaired electrons. So basically things like ionic solids, like you have this 11 F electrons, things like that. It's mostly coming from this inner shells of like F electrons. So like we discussed like erbium and PR kind of material. So so far we talked about these two effects. One is the Larmor diamagnetism. Then we talk about this ionic paramagnetism we call the Curie paramagnetism. So next we are going to talk about additional contribution coming from this free electrons of the metals. So far we only talk about due to this atomic properties, right? So either closed shell structure giving the Larmor diamagnetism or this Curie paramagnetism coming from this ionic unpaired electrons in like F electrons and things like that. So next we are going to talk about properties coming from free electrons in metals. So that we talk about polyparamagnetism. So this is all coming from free electrons. Then we'll talk about similar this free electron contribution for even diamagnetism. That's called the Landau diamagnetism. First, we'll talk about the polyparamagnetism. So this is, like I said, this polyparamagnetism is associated with the spin of the free electrons. So free electrons are valence electrons in metal, so they are loosely bound to the nucleus so that they can wander around the atom. So in crystals, they can be even associated with other atoms, right? Not just belongs to one atom. They can roam around other atoms. That's why we are calling free electrons. Yeah, naively one might expect that all the electrons align their magnetic moment with the external field, but that's not the case, because there's something has to do with how the electrons arrange according to their density of states. That also has the effect of the spins. So we know how density of state for 3D materials, so they change like square root of E, right? So then, so how this density of states for spin up and spin down electrons. So when we did standard density of states, we don't consider this spin, except we consider like you have two electrons states are available. But now if you have a magnetic field, we have to think about how the spin up and spin down electrons are going to be influenced by that electric field. So that will change your density of states for spin up versus spin down states. That's how polyparamagnetism is calculated. Like I explained here, you can see here on the left side, if I actually, this is not okay, talking about the density of states. So density of states, you can see if you have spin up, spin down electrons, so they have same number of spin up and spin down electrons. And if I draw my density of states, so remember they were like going like square root of E, right? So they have both square root of E. So then we have without magnetic field here, so no external magnetic field. So then they are filled up to Fermi energy. But now if I apply magnetic field, we know the density of states for this downward one is going to be increased, because some of the the electrons will spin to upward, right? So then so you are going to have some increase in your density of state for down states. So then the decrease of your density of states for the up spin. So still they have to change that one so that you have the same Fermi energy here. So this one actually shows you how that is done even in a more convincing way. You can see this is negative state. They have getting more spins because some of the even negative ones are getting positive. So then the positive one, they are getting less here. So you can see the difference between these energies. Each one will change by this energy mu BB, right? So this one mu BB, then this one also mu BB, then the difference will be 2 mu B, and that's the energy, right? Energy is given by mu dot B. So now if you calculate what is the difference between, so this some of the spin down ones, so then some up ones turn back to down one, so that minus, so down ones with some still with some up spin, so that difference between these dipoles will be given by your density of state for the density of state at the Fermi energy, right, multiplied by that energy mu B0. So now if you want to calculate the total magnetization, so then you have to multiply that magnetic moment by that's mu B. So this is the number of spins. So then multiply by your mu B. So then divide by the volume. So that is the total number of magnetic dipoles per unit volume. So that is your magnetization, right? So now if I substitute this function here into this one, you get m as, yeah, just plug in here. So this becomes, so you get mu b, an additional mu b coming here, mu b squared. So now if you know m, then you can calculate your susceptibility. So that's given this, you just divide by mu 0, right? So then you get, then mu 0 comes here, G. So this is your susceptibility. Remember, this is a positive value. So that means this is a poly, the paramagnetism, but coming from these free electrons here, right? So these are free electron contribution. So again, this is a very small value, but it's a positive value. Remember, lambda value, that's also very small. That's a negative value. So now we showed poly paramagnetism coming from the free electrons. So now we can consider this paramagnetism. Remember, we also talk about the Curie paramagnetism, right? So far we talked about three magnetic properties. One is Lama diamagnetism, that's due to the closed shell atoms. Then we talked about Curie paramagnetism, that is also due to the atom but unspin electrons like the F electrons. So that's what we had, that temperature dependence susceptibility goes like C over T. Then we talked about this poly paramagnetism coming from the free electrons. So if you consider this paramagnetism coming from the ions, that's the Curie paramagnetism. So that mostly because the magnetic energy is greater than your thermal energy, right? But polyparamagnetism happens because your this magnetic energy is greater than your Fermi energy. Because of that, your spin up and spin down spins will be adjusted so that your total the Fermi energy will stay constant for both spin up and spin down electrons. So that's the situation for these two. So then later Landau came along and calculated the diamagnetism from the free electrons. Just like Pauli's paramagnetism, he calculated the diamagnetism from free electrons. So then he found actually the value is almost same as the polyparamagnetism, except there's a factor 1/3. So then also diamagnetism, this is sign minus. So this derivation is little bit tedious, but it's all free electron theory. That's not too difficult. So then you can you have this factor, if the effective mass for mass. So if it is same, you can neglect this term. So now we have actually 4 contributions, right? Landau diamagnetism, sorry, Lama diamagnetism from atoms. Then we have Curie paramagnetism due to this electrons, sorry, the atoms. Then we have polyparamagnetism due to free electrons. Then we have Landau diamagnetism due to the free electrons. So we can write all these in one expression like this. You can see this is the diamagnetism term we call the Lama part due to the atoms. So then this first part is the paramagnetism due to the polyparamagnetism due to free electrons. This is the Landau diamagnetism due to free electrons. Then we have the Curie paramagnetism. If you want to put it here, that is that C over T terms, right? So your chi goes like plus. So these are the 3 terms in addition to Curie paramagnetism. So that is also coming as a atomic contribution. So actually, one can easily do this one in one simple quantum mechanical expression. So if you write the total Hamiltonian for electrons, you can write this a bunch of electron in this Hartree approximation. So you can write your Hamiltonian 1 over 2m, your p squared over 2m under magnetic field, we introduce this something called the vector potential, right? Vector potential is basically H is grad cross A, or A is given by half this R cross H. The A is called the vector potential. It's just like in electrical potential, that's the scalar one, right? So your electric field is minus grad V. So that V is called the electric potential, right? So here, this is vector potential. So B is grad cross A. So A can be written as this one. So that is your P squared divided by 2m. That's the kinetic energy term. Plus your next energy we can write as this magnetic field interacting with the spin. So later we will find this part will have orbital angular momentum itself, because that's a kinetic term, right? Orbital angular momentum comes from the momentum part. So if you have h dot s, actually if you expand this one, so how do you do this one? You can square this this term, then you have p squared, then you have this one e over c, then this one will be p dot a dot p. So that's the cross term. Then you have square of the second term. So now if you write this one, so if you consider h to be in the direction of z, so then I can write this one as this one we wrote before. So if you expand a little bit, so this A you can write as like that R cross H, because we define H like that. So if you substitute that one, so then yeah, so if you write this one again, A is R cross H, actually factor 2 also should be here, so don't worry about that one. So A is given by R cross H. So then if you do that one, you can easily find H is constant, H squared, then R squared becomes xi squared plus y squared. So here R cross P dot H, that if you do this one, what is R cross P? That is basically L, right? The angular momentum dot H. So now if you do this, yeah, that's what we introduce here. L. So if you proceed this one little bit further, you can write this one as this 1 over 2m, this pi squared, then you have this term becomes this mu b L dot H. So then you have this term, this is nothing but that Lama diamagnetic term. So now, so if you look at that's the this part. Remember in the Hamiltonian we had another part, this S dot H, right? So then your total Hamiltonian will be, so this is what we got from here. So then you had this last term, H dot S. So if you add these two, what do you get here? So you have, so if this is your the H0 for the free system, so then your the perturbation part would be, so here mu b L dot H, then you have, this is 2, right? 2 H dot S. So GE, so that dot H. So this is exactly what we got. So now actually you could get everything by simply expanding that simple quantum mechanical Hamiltonian, but you don't have the free electron contribution here. So then if you want to calculate the energies, you can simply use the standard first order perturbation theory. So if you do that, your delta E is given by, so you just calculate your expectation values. So you can calculate that one. So this is your diamagnetism. This mostly coming from your paramagnetism. So if you have atoms or ions with closed field shells, so then if you have closed shells means you can only expect the Lama frequency, right? So that's what these two terms become 0, because J0, L0, L0 will be all zeros for closed fields because there are no unspin electrons. So then you only get this term, that's the Larmor diamagnetism. So if you calculate this one a little bit further, so that is energy. If you want to calculate the susceptibility, because this is, remember, this energy term, right? If you calculate susceptibility, is nothing but second derivative with respect to H. If you calculate that one, you even get that factor 6 here. So this is basically that average distance between nucleus and the electron. I think they all are very consistent with what we have been talking so far. So if you want to summarize everything, so we know diamagnetism. So this is more like the Lenz law, right? So if you apply external magnetic field, your spins will arrange in the opposite direction, right? So that means your chi is negative number. So, but the this value is very much smaller than 1, so very small number. But in the paramagnetism, so all the magnetization will be in the direction of H. So that means your chi is positive, but still the absolute value is very small, much smaller than 1. So if I plot diamagnetism as a function, magnetization as a function of field and function of temperature, you can see your chi is negative, right? For diamagnetism, you get this kind of curve. For temperature, we don't have any temperature dependence for diamagnetism. But for the paramagnetism, if I look at my field dependence, we know it is a positive chi, so you have this kind of behavior. So then if you look at the Curie paramagnetic behavior, that shows T dependence of chi is the C over T, right? So C depends on your total angular momentum and everything. So that's basically the summary of this paramagnetism and diamagnetism. So, but next we are going to talk about something called ferromagnetism. So in both these cases, when you remove your magnetic field, these spins are going to be realigned and become non-magnetic. But there are something called ferromagnetic materials. Even without any external magnetic field, they will have magnetization. So not only that, the susceptibility, they are positive like a paramagnetism, but the value is much larger than 1. So that's the difference. So sometimes this ferromagnetics become something called the super paramagnetics. So that means they are no longer ferromagnetic, but still the chi value is much larger. So we'll talk about that one a little later. So this is the summary. So we talk about non-filled shells can lead to permanent magnetism by the total angular momentum J and the Lambda J factor. So that will give you paramagnetism. Also, when you have external magnetic field, you have diamagnetism as a response to the this Lenz law, right? So then we have an estimate for the both size of both type of magnetic moments. We have calculated mu c for both paramagnetic and diamagnetic properties. So next I want to talk about a little bit about this ferromagnetism, or sometimes we call spontaneous magnetization. So that means, so you have these magnetic moments, so they are even without magnetic field. So in paramagnetics, we know they are random, but applying magnetic field, you can make them align. So once you remove the magnetic field, they are again going to be under this thermal effect. So they are randomized, right? But ferromagnetics, even without magnetic field, they can be aligned. So they all lie in the same direction. So with the same magnetic dipole moments, so they call the ferromagnets. So then there are something with the spins, they are adjacent spins are up and down, so with the same magnitude, but opposite spins, so they are called the antiferromagnetics. So then there's something called special kind of this antiferromagnetism called ferrimagnets. Only difference is in that case, the adjacent spins are opposite, but their magnitudes are different. Like for here, this uphill spin is larger than down ones. So that means you have permanent magnetic moment here. So here it's in more clear way. So you have ferromagnets, adjacent ones are all parallel and they are same magnitude. Here, adjacent ones are opposite, but they are also in the same magnitude. That means your total M is going to be 0. So ferrimagnets, they are opposite, but magnitude is different, making it more non-zero magnetization. So typically ferromagnets are like iron, cobalt, nickel, these are transition metals. So antiferromagnets are mostly like these nickel oxides and some other oxides. So magnetize these iron oxides, they are some example of ferrimagnets. So here is a summary of these magnetic materials. If you take this iron, nickel, cobalt, at low temperature they are ferromagnetic, but if even room temperature they are ferromagnetic, but if you go to very high temperature, they become paramagnetic. They lose that permanent magnetization. So there's this temperature called Curie temperature. When you exceed that temperature, so then this the exchange interaction becomes less compared to the thermal energy. So then they become paramagnetic. So then we have this gadolinium, terbium. So this kind of materials, they are actually in the rare earth group. So they are ferromagnetic even below room temperature. At low temperature, they are ferromagnetic. Even at room temperature, they are antiferromagnetic, except gadolinium. Gadolinium is ferromagnetic even at room temperature. Most of the rare earths are antiferromagnetics at room temperature. But again, when you go to high temperatures, they are becoming paramagnets. For antiferromagnets, we have that special temperature called Neal's temperature. So above Neal's temperature, they lose that permanent magnetization, so that they are no longer ferromagnetic or antiferromagnetic. So for those of you, so typically transition metals are in this range here. So things like this titanium, vanadium, chromium, manganese, this region is mostly the transition metals. So rare earths are like ones we show here in this, like scandium, yttrium, lanthanum, and all that this row here. These are the rare earths. Remember we studied this erbium and this PR. They have all F electrons, right? So they are rare earths. So ferromagnetism, you can think as a special case of paramagnetism, right? Because they have individual spin magnetic moments. They interact with other spins. That's the whole idea in ferromagnetism. The spins, they interact with other spins. So that's we call the exchange interaction. So the uncompensated spins in individual atom ferromagnetism may couple either directly, they can direct, I'll talk about that one later, they can directly couple to other spins, or they can couple through intermediate anions like oxygen vacancies. So they can interact. That's called the super exchange. So that's how we explain the ferrimagnetism in this magnetite or iron oxide. So in ferromagnets, they have a net non-zero magnetic moment due to the coupling of spins, right? So that will keep them in preferred orientation because of that interaction that you don't have for paramagnetism and diamagnetism. Also remember that coupling is a quantum mechanical phenomenon. So happening between these neighboring atoms. As with ferromagnets, ferromagnets have strong positive magnetic susceptibility. Paramagnets have positive susceptibility, but very small, right? Less than 1. But ferromagnets have very high positive susceptibility. So in paramagnets, we know when the applied field is removed, they lose the permanent magnetic moment. But in ferromagnets, even after you remove, you have component of magnetization in the direction of the applied field. So that's a permanent magnet, right? So then also they have a special property called hysteresis. So then remember, diamagnets or paramagnets, they show the Curie law that is given by C over T, but ferromagnets have something different. It's not C over T, that is given by C over T minus some constant. So that constant is mostly the Curie temperature. So then that behavior is different than simple 1 over T dependence. So I think I will stop here and continue for the last part of the magnetism in the next lecture. Okay.